Welcome back. This is Larry Banco, and today's video compares conventional transformers and auto transformers in radio frequency applications. There are some subtle and important differences that you hopefully will find interesting. But before we get started, the current version of SimSmith did not allow parameters in the auto transformer to be remotely controlled, so I waited until a new version of SimSmith was released. The current version of SimSmith is version 16.8, and that's the version I need for this video to operate correctly. If you're not sure what version you have, or if you want to check at any time what version is the latest version available, click on SimSmith, visit website, and when the website comes up, scroll down a little bit, and you're given two choices. Version 16.8 is the latest version. We'll click on that in a second, but version 15.1 was the last version that used the old .ss file format. If you're not sure whether you want to have this version also installed on your machine, look at my video number 75. Number 75 describes the difference between the versions and why you might want to keep the old version around if you're looking at some of my older videos. But click on version 16.8 for the current version. And the second file here is 16.8AB. That's what I have, and that's the latest version. If you do not have the latest version, it's a good idea generally to get the latest version. SimSmith is totally free. And this is the version for the Mac. This is the version for 64-bit Windows. This is the version for 32-bit Windows. This is the version for Linux. And if you want to, and you have the Java runtime environment installed on your machine, you can download just the .jar file. When you do that, when you do any of these installs, you have the choice of putting the version of SimSmith in a new folder or not. If you put it in a new folder, you'll have both versions of SimSmith active on your machine. You can run either one. I generally put the new version in the same folder where the old one was, and it overwrites it, and I only have the one version. So anyways, it's easy to check. SimSmith does not go out and check for you, and SimSmith does not automatically download new versions. So that's pretty much it, all you need to do, and let's get started with the video. SimSmith gives us a few different ways that we can compare circuits, and one of them is to run multiple instances of SimSmith, and that's what I've done here. The first instance of SimSmith is showing a conventional coupled transformer. The second instance is showing an auto transformer. These two instances of SimSmith are both independent. I can do anything I want in each instance, and it doesn't affect the other one. For this example, I'm going to match 25 ohms to 50 ohms over the range of 1.8 to 54 megahertz. And the goal is to see the difference between the two different transformer types. Now, there's an easier way probably to do this since the circuits are simple. And the easier way to do this is just to, instead of running two instances of SimSmith, just to run one instance of SimSmith. And this one instance of SimSmith is divided in two parts. SimSmith allows us to have a load generator block, and the load generator can clone the generator here, and it can clone the load here, which is what I've done in this case. So we have two generators, they're both identical, two loads, they're both the same impedance, and we have two different circuits. This allows us to sweep parameters of each of these two circuits at the same time, and that's what I've done. So the control block takes two parameters, the inductance looking from at the right side of the transformer looking in with the left side open, and the inductance looking in from the left side with the right side open, and it sets those to be the same value for both transformer types. And it also sets the load impedance based on the standard circuit impedance, which is the center of the Smith chart, times the ratio of the left over the right side inductance, which gives us what the 25 ohms here. And this assumes a coefficient of coupling of approximately 1, but I'm just setting this. So if I change this value, the load changes automatically, and it's just kind of a convenient way to do things. At first glance, it might appear that these two circuits are identical. And let's look at it a little more closely and see if that's really the case. The impedance seen by the generator looking into the auto transformer can be plotted on the Smith chart by clicking on A. A is enabled. We see this plot. This plot starts with the little dot at the low frequency. I'm sweeping now. So I'm sweeping from 1.8 to 54 megahertz. This is the 1.8 megahertz impedance. We can click on this plot, or this chart down here, and change the meaning of it. So we start with impedances. This converts it to a parallel impedance form. This is a series impedance form. This is more chart parameters, and back again. we see it's 50 ohms in parallel with 10 microhenries. 10 microhenries is exactly what we expect to see because that is the shunt inductance of this inductor, and that's in parallel with 50 ohms, which is the 25 ohms transformed to 50. If we look at the conventional transformer, we see, by plotting to point B, exactly the same impedance plot. Now these circuits have the same impedance, but remember that this circuit is capable of being isolated. It's shown as being with a connection down here, but you could easily disable this connection and this transformer would work exactly the same way. And sometimes you need to do that in your circuit. Sometimes you need to have like maybe a DC voltage on one side of the transformer and the other side is some kind of a generator that only can source current or sink current or whatever, and you need the other side to be connected to ground. If you need to do something like that, you cannot use an auto transformer and you're stuck with a conventional transformer. However, many cases, or maybe even most of the cases, an auto transformer works just fine. You don't need that isolation. So let's look at the power delivered into the load. The power delivered into the load through the auto transformer can be plotted by plotting L. We see that in this case it's a 100-watt generator, and we're plotting versus frequency. We see at all frequencies it's pretty much 100 watts, and at low frequencies it drops a little bit. It drops a little bit here due to mismatch loss, and we see that by plotting SWR. We see the SWR coming up to 1.55 to 1 at low frequencies. Not within what I wanted to have for a spec, but this is what we have at the moment. If we plot this transformer, we see the power delivered into the load is exactly the same as the power delivered into the load for the auto transformer. And we see the SWR looking into this conventional transformer from the generator as being exactly the same SWR as we saw with the auto transformer. So from that point of view, these two circuits are identical. However, let's look at the currents that are flowing in the windings. The current that flows in the winding, the primary winding on a conventional transformer, can be plotted as B dot capital I. That's the current going into this component. We plot that, and I'm plotting it by this command. RMS stroke 3, I made the line a little bit wider for ease of being able to see on the video, and I'm plotting B dot I. Since I didn't give it a label, that's what it gives me. It gives me what I actually plotted. And we see that that is 1.41 amps. 1.41 amps squared times 50 ohms is 100 watts. The output current can be seen as LG1 dot I, that's the current flowing into the load, and that is 2 amps. 2 squared times 25 is again 100 watts. No power lost here. Actually, this is 99.8 watts. Now let's look at the auto transformer. And the auto transformer, the input current is A dot capital I. And I hope people are following this because I've talked about plotting before and all the commands you can plot. And SimSmith is really good about this kind of stuff. But unfortunately, if you don't use it regularly, it kind of looks a little cryptic. But A dot I you see as being right on top of the primary current for the conventional transformer. So this current right here is exactly the same as this current right there. And the output current, which is L dot capital I, current into the load, is exactly the same as the output current of the conventional transformer. Now, what's the current in this winding down here? We know from circuit theory that at any point in a circuit, the sum of the currents at any node, which would be right here, is 0. This current flowing into here is A dot I. This current flowing into here is minus L dot I, because the current flowing out of here was L dot I, so the current flowing in is minus L dot I. So A dot I minus L dot I will plot the current in this lower winding. And lo and behold, it's a much lower current. This means that we're capable of using a smaller wire gauge if we wish to for 70% of the turns. Remember that this transformer is set up to be an impedance ratio of 2 to 1, which means that the turns ratio is the square root of that value. So it's 0.707. So this is 70% of the turns. SimSmith is very, very good. If you watch what I do as I change this inductance, it'll move the tap point, and the tap point represents pretty much reality. We see if we get a tap point that's halfway in the middle, it's 1/4 of the impedance, which is exactly what would happen if the coefficient of coupling was close to 1. But nevertheless, what we see here is we see a significant improvement in current, lower current, which allows us to use a smaller wire gauge. Now, you might not want to care about that for a very small transformer, but if this was a transformer that was trying to handle 1,000 watts, having the ability to have 70% of the turns be a significantly smaller wire gauge might be advantageous to you. That's point one as far as, we had the isolation as being a plus for this transformer. Now we have the ability to use a smaller amount of copper to do the auto transformer. And this part of the winding right here has to, of course, match the same current that this winding has over here. So we don't save there, but that's only 30% of the turns. Now let's go back to the original Smith chart again, and let's turn this circuit into a little bit more of a real circuit. The coefficient of coupling of 1 is just an unreasonable number. Nobody can achieve that. It's the holy grail. And let's drop this down to, say, 0.99. At 0.99, we see a significant difference in the two circuits. Where they were the same when the coefficient of coupling was 1, they're not even close to being the same when the coefficient of coupling is 0.99. The SWR at 54 megahertz is 3.6 to 1. And you would say this transformer is unacceptable over that frequency range. Let's ignore that transformer for a moment and look at this transformer. What can we do to get this transformer to have an input SWR that's within this 1.2 to 1 circle? And the answer to that is there's two things we can do. We need to fix the low frequency problem. And we can fix the low frequency problem by raising the amount of inductance in this transformer. Remember, though, that the model for coefficient of coupling looks like this. And what this says is that some percentage of, you can think of a winding, and these two windings do not need to be the same inductance, but a percentage of this winding gets coupled perfectly to a percentage of this winding, and the other percentage of the winding doesn't couple at all. In all told, that gives you an average coefficient of coupling that's the right value. But if we think, this lets us model it easier. So for a coefficient of coupling of 0.99, 99% of the turns would couple perfectly, but 1% of the turns, which would be a fractional turn probably, but 1% of the turns would be effectively uncoupled. And this uncoupled inductance is called leakage inductance. It exists on both sides of the transformer, and it's the bane of any kind of high frequency performance. Now, the overall inductance is the problem that you get with low frequency response. So we have to try to come up with a happy medium. So in this case, the happy medium would clearly be to increase the inductance and allow the leakage inductance to go up. But I don't really want to do that. Well, I can do it. I'll do it for the purposes of just doing it, but you don't want to do it just willy-nilly, because what we're going to see is okay, now we've made the low frequency performance good, and high frequency performance isn't as good in this auto transformer. This is a lot more turns. If we need more turns on a transformer, maybe that's okay, but generally fewer turns is better a lot of times. And the auto transformer, while it's okay. Look at the conventional transformer. It's got an SWR now that's just terrible with those kind of inductances. It's got an SWR 15 to 1. So this isn't really a good solution. A better solution is to obviously try to compensate for something over this range. And that's what I'll do here just in a second. But let me go back to where I was. The difference between these two is a huge difference. And the huge difference is due to the fact that this 70% of the turns in this winding does not need to have any coupling. It's the same, it's just current in this winding. It means that if I want to make this performance of the conventional transformer match the performance of the auto transformer, I need to increase the coefficient of coupling some. So let me increase it until they get pretty much the same value. That's very close for the two. 1% of the flux was lost in this transformer. The 1% didn't couple, so it just went out in the air. So 1% of it didn't couple. In this case, 0.09%. That is like 11 or 12 times as much flux could be lost in this transformer versus this transformer. It gets harder and harder and harder to achieve a coefficient of coupling of 1. This is an incredibly hard number to do, and you'd probably struggle and never achieve this. Over here, 0.99 is not that hard to do. And as we'll see, we can even make it even less than that if we want to. So let's take this transformer and reduce the inductance even more. Let's reduce it, say, to 8. Let's reduce it to 6 microhenries and 3 microhenries. That's a huge amount. Now, the low frequency performance is absolutely terrible. Let me get rid of that. Low frequency performance is absolutely terrible in this transformer. It is a SWR of 2.06 to 1. But if I compensate for it with some series capacitance, and I need to plot at C2 now because that's what I want to look at. And this looks ugly because of the sweep points. But I need to increase the capacitance quite considerably. I find this kind of therapeutic watching watching things come into as desired in the Smith chart. Okay. So now I have a pretty good performance here. And if we look at this closely, what we'll see is this capacitance value and this capacitance value should vary by about a factor of 2 because the impedance is varied by a factor of 2. This is the high impedance side, so it needs less capacitance, so it's a lower capacitance side. But now I've got pretty good performance. What can I do now? I'm willing to tolerate at the high frequencies an SWR of 1.2 to 1. Well, heck, I don't need coefficient coupling of 0.99 anymore. I can easily deal with a lower coefficient of coupling. 0.974. Now we're starting to talk about a transformer that's easy to wind. This transformer is quite easy to wind. Let's look at what we need to do in this transformer to achieve the same goal. This is going to get a little ugly because I'm going to have to make the components a little bit smaller so we see things still well. I could have shrunk some of these to 0. It wouldn't have mattered. But disable that one. And now we see the coefficient of coupling looks good for this transformer, the conventional transformer. But what we want to do is we want to relax the requirement on coefficient of coupling. I think I misspoke just a moment ago. So now let's compare the two. This one needs to be 0.974 or 2.6% of the flux is lost. This one is 0.9978 or 0.22%. This is still better than 10 times more flux can be lost and still get the same performance. So this is a huge deal. This is the reason why people use auto transformers at RF. And here's an example of doing just that. This is a little mini circuits 2-to-1 splitter or 2-to-1 combiner, where this is the split or combined port, and these are the two standard ports. So we have a little bifilar wound transformer here, which does the combining or splitting, and it converts the impedance at these 2 points, which is 50 ohms, into a 25 ohm point here. And this 25 ohm point here needs to be converted back to 50. This little transformer right here is a 22.22 to 50 ohm transformer. It's trifilar wound. We see a red, green, and a kind of a gold color wire. It's trifilar wound with one of these turns being on the top side of the transformer, 2 being on the bottom side. So instead of being a 0.707 to 1 ratio, it's a 0.66. That means the impedance is a little bit wrong, but as we'll see in just a second, that really isn't that big a deal, and this enables us to get very high coefficient of coupling, and this transformer works from 10 megahertz to 1,000 megahertz with an SWR of better than 1.2 to 1. So let's go back, take this circuit again, just get rid of some of these components. Let's set this to be a more reasonable value, and I will not do much more with it than that. This is the impedance that we get with this transformer, and let's set this to be a 1/3, 2/3. So 1/3, 2/3 means this is 4/9 of the overall inductance because it's squared. So this would be 4.44 microhenries. And this adjusted it to 22 ohms, which I didn't want. So let's just turn this off for the moment and set this back to be 25. So instead of putting us down here at the center point, it puts us up here. However, this little transformer that I showed a minute ago had some other components that were compensating for this. And they would do things like bring the overall SWR range, overall impedance range down here. And that's what that transformer actually did. So, I mean, I could play the game right now if I raise this coefficient of coupling up somewhat. So raise it up like that. And I need to compensate for the low frequencies again. All right, now I see that I'm within the 1.2 to 1 SWR circle that I wanted to be in. And the capacitors are actually fairly easy capacitors to come by. Now notice, and this is a little trap here for people who aren't real familiar with SimSmith, I can click on this now and I can get the voltage across the component or across the, which way we're going. We're going vertical, or are we going across the component? I want to go across the component. So I see the capacitor out here being a 1.3 at 1.8 megahertz. It's got 1.3 amps of current in it. It's got 18 volts across it. This capacitor has 13 volts across it. 50 volt capacitors would work just fine here. These capacitors will have lower voltage across them at higher frequencies, of course. But it's not very hard to come up with a capacitor that's got good performance up to 54 megahertz. Any little ceramic capacitors will do it, surface mount ones. A couple of them in parallel to give me this value and a couple of them in parallel, and these values aren't that terribly critical. If I go up and down 10% in this value, we see nothing really, not that much changes. So these are easy to do, and they don't really have any cost associated with them, and we get pretty good performance on this little transformer. This is all I really wanted to show in this video. But if you'd like to hang around for some more, I was going to show how to put an auto transformer in a ruies block, because this particular component cannot be put in the ruies block. You have to manufacture the auto transformer yourself. If you're not interested in that, that's fine. Thank you very, very much for watching the video. Please click on the like button if you like it. Please subscribe if you haven't subscribed. If you have subscribed, but you expect YouTube to give you notifications, the new algorithm in YouTube favors lots of different things than it used to, and you might not get notifications. You can always click on the bell and you'll be notified of every new video I do if you wish to do that. Anyways, thank you again. Well, if you're still with me, here is a SimSmith schematic showing an auto transformer using the auto transformer component and an auto transformer within a ruies block. And they are exactly identical. Now here's the auto transformer in the ruies block. And let's discuss it for a moment or two and see if what we can come up with. Again, the control block here does nothing more than set the value of the right side and the left side inductance and the coefficient of coupling. Then after that, all the processing is done inside the ruies block for the transformer itself. So you can see that I set component A and A1, the right side, the left side, and the coefficient of coupling. Now, this circuit shows 4 resistors. These resistors perform an up-down function. So when the impedances are such that this is a step-up transformer, the up resistors become 0 ohms, and when it's and the other ones become 1 gig ohm. And we can see that right here. If I go, let's set this to where it's almost 1-to-1. We see that this is still a step-down transformer. So 10 microhenries on the right side, 9.5 on the left side, still a step down. So the down resistors are set to be 0 ohms, which means they're in the circuit. The up resistors are 1 gig ohm and they're out of the circuit. As I go to 10, I see it switch. Now, it switches right at 10. It could have been, so if we had done this 9.99 or 10.01, it doesn't really matter at 10 which way it's connected, because at 10, there is effectively, the tap is all the way up at the top anyways. But we can see that it switches like it should, and SimSmith switches too. If you watch the little symbol at the top of SimSmith here, we see it there. Now we have a step up. Get down here to 10, it's nothing more than a shunt inductor, and below 10, we see the the step up. So there it's a step down transformer, higher impedance, lower impedance, and on this side it's lower impedance and higher impedance on this side. So this circuit does exactly what you'd hope it would do. It's a little bit interesting how it works. But so what I come in here and do is I ask myself the question. First of all, I say coefficient of coupling. I'm going to couple these two coils together with K, which we know we need to do. But what are the values of these two coils? They aren't 10 microhenries and 5 microhenries. They're the effective values. And that's what SimSmith is calculating here with the upper and lower values. So in order to calculate the effective values, I do this formula right here. And this formula is based on this. And the total inductance in a string like this, if you broke this string up to be a coupled inductance and a leakage inductance, the upper inductor would have a 1 minus K times the upper inductance value. That would be leakage. Then K times the upper is the part that gets coupled to the K times the lower value. So we take the square root of that. That converts it into effectively into turns. We take the turns, we add the turns up, we get it, and then we square it again and get back to inductance. And this assumes this only works if the coefficient of coupling is 1. But remember, these are the turns that actually have a coefficient of coupling of 1. Even though K is involved in here, the coefficient of coupling is 1 for this effectively coupled fraction of the turns. So we take that, we square it, and then we add the leakage on the other end. Now this formula, if we take this and solve for upper, there's a whole bunch of algebra involved, and I'm not going to do it, but I did it. It took me a few hours to get it right, but we get this formula right here. So now I have a formula for upper. So I can calculate the same upper value that SimSmith calculates. The lower value is always equal to the value you see when looking in from the appropriate side. So the lower value is 5 microhenries here, and if we move this up the other way, we see the lower value is always 10 microhenries on this side, because that's what we have it set to. And if you'd like to just take this formula, let me make it big here. Capture it, put it in wherever you want to put it somewhere, and use it. It works just fine. And to demonstrate that, I can plot the impedance seen at the generator for the component SimSmith has, and the impedance seen at the ruies block component. And I built these components over time in an attempt to try to find faults in SimSmith, and some of these were used to find the faults that I did find recently in SimSmith for the auto transformer. But the auto transformer now is solid in version 16.8. And we see that it doesn't matter what the coefficient of coupling is. The two curves are on top of each other. It doesn't matter if it's step up or step down. Again, the two are the same. We can plot the power at the output. The power at the output is the same no matter what. And this is a good simulation. Now, just one little thing. SimSmith allows us to take a ruies block and save it through the Explorer here, but I don't generally do that. What I do is I save these components in schematics. And if I ever want to take this, I'm not sure if people will realize this, but let me bring up another instance of this exact same SimSmith file. This one I'm going to take and delete the ruies block. I can copy, and of course this fails now because we look at this. What we see is there is no A1 component anymore. So ignoring that for a moment, I can drag ruies blocks. This is a little bit aggressive of me. Let me do it this way. I can drag ruies blocks from one schematic into another directly now. I don't know when that actually happened in SimSmith. It's been in there for a few versions. But rather than saving ruies blocks to a .ccse format, which you may do, and you can do, I just leave them in schematics. So I have a schematic that has all kinds of components in it, and I just drag these components out when I need them. So I've got a schematic that has many different attenuators in it if I want to use an attenuator in a circuit. I've got one that's got various transformers in it that I drag out. But that's just a little tip if you're into doing stuff in SimSmith a little bit on a higher level. Anyways, if you stayed with me, let me know if you actually liked this additional piece of the video or not, or whether it was just a waste of time. This rules block also allows me to set the Q of those inductors. The Q is set in this component nominally at 1 million, so I set it to 1 million here, but the Q could be set in my block independently. And of course, if you wanted the Q on either of these inductors to be different, you could make the Q different on those inductors. In the case here, that's just the value Q, but I could have made a Q1 and a Q2 if I wished to also. Anyways, same thing I always say, let me know if you have any suggestions for videos or whatever, and thank you for watching.